Hi, this is Dr. S, and this is video 9 in my series on reaction rates for Year 13 A-Level Chemistry. In this video, we'll look at how to determine the order of reaction with respect to different reagents from initial rates data. So we've looked at initial rates experiments in previous videos. Let's just see at what data that can give us and how we can use it. So the whole idea of an initial rates investigation is to sequentially change the concentrations of different reagents and see what sort of effect that has on the rate. So for example, if I had a reaction in which we had X and Y reacting together, then what I could do is I could do a baseline experiment in which I maybe had 0.1 mole per decimeter cubed of X, 0.1 mole per decimeter cubed of Y, and then I would determine the rate of reaction. Let's say that was 2.0 times 10 to the minus 4 moles per decimeter cube per second. Now what I would do is keep the concentration of one of the reagents the same and change the concentration of the other reagent. And then I know that any change in the rate is purely down to that reagent. So for example, let's say we kept Y at the same concentration, but I doubled the concentration of X to 0.2. I then find out what effect that had on the rate. So let's say that the rate went up to 4.0 times 10 to the minus 4. What I could see there is that the doubling effect of the concentration of X has had a doubling effect on the rate of reaction. So I know that the rate is proportional to the concentration of X. So it is a first order reagent. So X is a first order reagent. Then what I would do is I would keep the concentration of X constant with one of these experiments. I'm going to keep it constant with the first one. I'm going to go back to 0.1 mole per decimeter cubed, but I would change the concentration of Y. And here, if you look, what I've done is I've kept the concentration of X the same between experiments 1 and 3, but I've doubled the concentration of Y. So now let's have a look at the effect of the rate. Let's say that the rate is now 8.0 times 10 to the minus 4. Well, we know that the concentration of X is the same between these two experiments. We're comparing experiments 1 and 3. The concentration of Y has doubled and the rate has gone up by 4 times. Well, 4 is the square of 2. So that means that the rate is proportional to the square of the concentration of Y, meaning that Y must be a second order reagent. So we know that X is first, Y is second. So let's just go through how we've proven that. We've said that as the concentration of X doubles, the rate doubles. Therefore, we say that order with respect to X equals 1. It's first order. As concentration of Y doubles, the rate multiplies by 4. Therefore, order with respect to Y equals 2. We can sometimes use WRT as a shorthand for with respect to. Now I know the orders, I can put together the rate equation. So I know that would be rate equals K X Y squared. Then I could calculate the rate constant by rearranging. So K equals rate over X Y squared. Put in my numbers. Now to select the numbers, you would pick any one of these experiments. You should get the same number for each experiment. It's normally a good rule of thumb to pick number 1. So I'm going to use the numbers from experiment number 1 here. So 2 times 10 to the minus 4 divided by 0.1 times by 0.1 squared equals 0.2. Then we go back to thinking about the units. This is a third order reaction, so when you work out the units, you should get units of dm to the 6 mole to the minus 2 s to the minus 1. Okay. Right, so I'm going to put 2 examples on the screen for you to have a go at. So I'll put them on, pause the video, have a go at them, and then come back when you're ready. Okay. So let's have a look at the first one. So on the first one, what we should be looking at is, this is my baseline experiment. What has happened between experiment 1 and experiment 2? Well, the concentration of A has remained constant, but the concentration of B has doubled. What's happened to the rate as a result of that? It has doubled. So concentration of B doubled, rate doubled, order with respect to B equals 1 because it's proportional. Let's have a look at A now. We can see that the concentration of A is now changed to 0.250. But we have to be careful which experiments to pick here. We want B to be consistent. So we're going to pick 1 and 3 because the concentration of B doesn't change. But the concentration of A is halved. What happens to the rate as a result? It's halved. So as the concentration of A halves, rate halves. So order with respect to A equals 1. So we can work out the rate equation. Rate equals K, concentration of A, concentration of B. We rearrange, put our numbers in again, picking the top row. We would get that K equals 4.6 times 10 to the minus 3 divided by 0.5 divided by 0.4, and that equals 0.023 dm 3 mole minus 1 s minus 1. Okay, second one. Concentration of D has remained constant between experiments 1 and 2, but the concentration of C has tripled. Let's have a look at what's happened to the rate. If you do 1.134 divided by 0.126, you should get that the rate has multiplied by 9. Well, 9 is the square of 3. So that means C is a second order reagent. So concentration of C multiplies by 3, rate multiplies by 9, order with respect to C equals 2. What happens to D? Well, let's look at here because C remains constant. Concentration of D is doubled. What's happened to the rate? Nothing. So it shows that the rate is independent of the concentration of D. The concentration of D doubles, rate stays constant, order with respect to D equals 0. So our rate equation is rate equals K C squared. And again, using the numbers from the first experiment, we would get 0.126 over 1.2 squared equals 0.0875 dm 3 mole minus 1 s minus 1. Okay, I hope you got those. In my next video we will look at slightly more complicated examples of these where you might have 3 reagents or where you might have to use orders you've already worked out to work out another one, which is more complicated. I'll see you then.